So, good morning, everybody, and welcome to this presentation, in which I will talk about our work on floating point runtime variable precision applied to iterative methods, specifically for energy efficiency optimization. My name is Nordin Said, and this work is supported by the laboratory of TIMA and by the University of Grenoble-Alpes. Before we start, I will introduce the context of our research. In our case, we target CPU-based architectures, mainly open source RISC-V implementations. More specifically, we focus on floating point computation optimization. And as you know, floating point units are available in most CPUs nowadays. Since they boost the performance, they enhance software portability and flexibility, and they also take less development time compared to other arithmetic systems, such as fixed point, for example. However, FPUs add an extensive power consumption overhead. We want to reduce this overhead while keeping all the advantages brought by floating point. And as you know, a floating point number is defined by three fields. So there is this sign bit. We have also the exponent field, which represents the dynamic range, and the mantissa field, which represents the numerical precision of the representation. So one can reduce the overhead by reducing the bit width of these two fields using either IEEE 754 formats, so float, double, etc., or by crafting arbitrary reduced formats. For example, if we don't need much precision, we can reduce the bit width of the mantissa M. Or if we don't need a vast dynamic range, we can also decrease E, for example, which is the exponent bit width. So in the paper, we illustrate this with a use case, which is the Jacobi Iterative method. Here we have to solve a linear n by n system in the form AX equals B, where A is an n by n matrix, and B and X are n vectors, and we are trying to solve for X. So Jacobi consists of decomposing the matrix A into a diagonal component D, a lower component L, and an upper component U. And this leads to this iterative solution over here, where X at the iteration k plus 1 is computed as a function of the previous approximation X of k. So the idea is to start with an initial guess X0, and then compute X1, then X2 until convergence. In the right here, we represent the algorithm, which takes as an input A, B, and the initial guess X0. So we assume that the matrix A is strictly diagonally dominant, which ensures the convergence of the system mathematically. And we can detect the convergence by computing a metric expressed as the distance between two consecutive iterations X of k and X of k plus 1. So basically, we compute X at iteration k plus 1. Then we compute also the metric, and we repeat this process until the metric becomes less than the specified tolerance threshold tau, or if the maximum number of iterations, max iter, specified as a parameter is reached. Now, if we implement this algorithm in floating point double precision, we would obtain this convergence profile right here. This is basically the variation of the distance metric with iterations. And as you can see, the distance metric, which represents the accuracy of the solution, starts at around 10 to the power of minus 1, and then gets refined step by step until it reaches 10 to the power of minus 60. Meaning that this iterative process does not actually need a full precision since the beginning. And moreover, so the natural question that comes to mind is, if this is the case, why even bother computing with high precision if it is not actually needed since the beginning? It could have been, for example, way more optimal if we could start with a very tiny precision, say, for example, an 8-bit mantissa, and then increase the computation precision gradually as we get more and more accurate. So, for example, to a 12-bit mantissa, then maybe to 16, and so on and so forth, gradually until convergence. And when we approach convergence, we can then switch to full precision, which is a 52-bit mantissa, in order to refine the final results. Now, to answer the question that we asked earlier, why isn't this done already in current general purpose processors? And the answer is actually simple. The answer is because there is no hardware support for such behavior, and we will show that later in the related works. And this is the problematic actually that we are trying to tackle in this paper. How can we achieve arbitrarily reduced variable precision at runtime during execution? So in the remaining of this presentation, we will see first some related works, and then we will present the proposed hardware architecture that supports multiple precisions. We will see how can we transform the Jacobi algorithm to support variable precision in time. We will also see some results and conclude with future works. So in the literature, there are many works about what we call variable type optimization, VTO, which consists of carefully downcasting the maximum number of floating point variables from high precision types such as double and long double to lower ones, to lower precision ones, such as float, for example, as illustrated here. So these works are mainly search heuristics based on delta debugging. Some of them enable automatic source code transformation. However, they are data dependent, and most of them only support standard precisions. So they can only perform coarse-grained optimization. Other tools and libraries such as GMP, MPFR, FlexFloat, all these bring support for non-standard arbitrary precision. So they enable a fast simulation of arbitrary variable precision. However, these are also only intended for simulation and they don't provide hardware support. So the software still runs on high precision hardware and there is no actual energy efficiency gains. Other works studied variable precision in time, so we call that VPT, which enables precision variation during execution. However, these tools are also only intended for simulation. So on the mathematical side, there are also many works on mixed precision in linear algebra workloads. And this is a well-defined problem. However, through the years, it has been always tackled only with standard precisions. So there is still room for a lot of improvement thanks to reduced variable precision in time, VPT. So in this context, our contributions are the following. First, there is the design of an FPU that enables variable precision in time with a lightweight, minimally intrusive software support and no need for a specialized compiler. We demonstrate the effectiveness of our approach by proposing a transformed version of the Jacobi algorithm, which takes advantage from this FPU to leverage fine-grained energy efficiency. We also implement the FPU on a 28 nanometer FDSOI technology in order to demonstrate the resulting energy gains. So now we will talk a bit about the proposed hardware architecture. So in order to enable multi-precision computation, we propose the following architecture. It basically contains the original FPU here extracted from the open source Ariane RISC-V core. We have basically two main parts. So we have the standard part and then another, an approximate part. So this part here contains non-computational operations such as conversion and comparison. A second block which executes the square root and division operations, then fuse multiplication addition FMA, so FMA blocks in 32 and 64 bits. To support reduced precision computation, we added a third block, D, which contains reduction blocks that cast the original inputs from either float or double to an approximate reduced precision EI-MI with I between 1 and P. Reduced precision operators that execute the operation in the reduced format. And then we also have an extension block which allows to convert the result back to the original format. So the RTL is written in system Verilog and is parameterizable at design time. The pipelines decide these blocks are also configurable at design time. So we also added a set of control and status registers to control the precision of the FPU and its status. Now, at execution time, an assembly instruction can be executed either on the standard path or on the approximate data path, depending on the configuration of these registers. So basically, we have a status register, then a register that controls the precision of float operations, and then another one for double operations. As for the software level support, we developed a lightweight hardware abstraction layer that facilitates registers manipulation. So it's just a header-only library that can easily be included in existing applications. Now we can talk about how to transform Jacobi, the original Jacobi algorithm, from fixed precision to runtime variable precision. So if we get back to the Jacobi algorithm, we can actually now enable variable precision in time thanks to the underlying FPU architecture that we just presented. And to do that, we modify the algorithm as shown here. So first, we should define the available precisions that are supported in hardware. These are M1, M2, up to MP. So we have P total precisions. And each precision MI will be triggered when the metric reaches its corresponding threshold tol I. So first we enable VPT feature. Then we add an outer loop where we set the computation precision to MP. And then we perform the same iterations as in the original algorithm, but this time with reduced precision MP. And we do that until reaching the intermediate threshold tol P instead of tol. So we use tol P instead of tol associated with the precision MP. Then we repeat this process until we reach either the highest supported precision or the maximum number of iteration, max eta. So when this is true, we increase the precision and repeat the process until the highest supported precision is reached, and then we return the final result. So now let's compare the results of the two algorithms when applied to the same inputs. What we get is this red curve, which represents the convergence profile of the VPT algorithm. We can see that it behaves similarly to the reference convergence profile. And we can also visualize the precision variation on the right axis, which confirms that indeed, using this technique, we obtain the same results. So the same results with a much, much lower precision that varies automatically at runtime. So now, after verifying that the methodology works, let's evaluate the energy gains brought by this technique. So a quick word about the evaluation methodology. So the RTL proposed here is synthesized for an ASIC on a 28 nanometer FDSOI technology node. The supported reduced precisions and internal pipelines are configurable at synthesis time. Post-synthesis simulation takes into account all the activity, so the activity of the application, and the results that are presented here only concern the computation part that occurs inside the FPU. So everything related to memory transfers or caches or system parameters is not accounted for in this work. Regarding hardware level results, in the first row here, we have different target convergence thresholds tol, so 10 to the power of -8, 10, and 12. In the next row, we have the floating point variable types used in the source code, either float or doubles. So here it's all doubles. Next, we have 3 architectures named here, VPTE, VPTF, and VPTG. So each one of these configurations are generated with a set of intermediate precisions. So for example, for VPTE, the architecture VPTE supports the precisions 4, 8, 12, up to 28. VPTF supports the same, so the same precisions, but also adds support for 32 and 36. So it's always multiples of 4s. For all these configurations, the exponent bit width is always set to 11. Now we can first see the area overhead, which is very costly due to the added hardware blocks compared to the reference FPU. Obviously, we added hardware. So for this architecture, the area overhead ranges from 1.78x up to 2.6x. However, if we examine the power savings, we can see that we gain up to 64% in power efficiency, thanks to the use of only reduced precision and aggressive clock gating applied to the non-used blocks. Similarly, for computation execution time, it ranges from 45% up to 64% in this case. This is due to the fact that the number of pipelines used inside the approximate operators is actually decreased. So the same for computation energy consumption. We are here in the range of 80 to 87%, which is a considerable amount of energy. Now, if the requested tolerance threshold is reasonably low, for example, 10 to the power of -4 or -6, we can also apply traditional VTO. So just quick reminder about VTO. It consists of migrating variables from high precisions to lower ones in order to optimize the data transfers. Concretely, here, VTO consists of changing all the variables in the source code from double to float in order to optimize memory transfers. So if we evaluate this possibility too, the advantage is that we can also reduce the area overhead by decreasing the exponent from 11 to 8. For example, here the area overhead is reduced from 1.27x down to 1.19x. Power, execution time, and energy savings can also be decreased. So the gains can be increased a little bit, but the most important here is the effect on memory transfers. So a word about our future works. What we would like to work on for the next few months is to first optimize the hardware area by combining some blocks in the current architectures. We will also work on evaluation at the system level, taking into account memory transfers and system parameters. And also exploring the opportunities in other kinds of applications, such as image processing, machine learning, and neural networks. As a conclusion, standard full precision is over-designed for many classes of applications. We've seen here iterative algorithms, but can also apply to others. Modern workloads need also environments with runtime variable precision for further fine-grained optimization. So here we can actually always apply traditional VTO for coarse-grained memory transfers optimization, and then add another layer of optimization using the proposed VPT approach for fine-grained computation optimization. And then we also saw that iterative algorithms are perfect use case of VPT, a natural perfect use case of VPT, where we can change the precision during execution naturally. Thanks for your attention.